Hi, everybody, and welcome to Neuroscientists Talk Shop, UTSA's neuroscience research podcast. We're back after our summer break, and we're lucky to start this season with a special guest, Michael Mauk, who is professor of neuroscience at UT Austin. Mike studies the cerebellum, and I say this in a really general way because he studies everything about the cerebellum, from the behavioral measurements, the synaptic plasticity, the arrangements of synapses and the circuits and how they work together, and computational models that pull all of that together. And we probably won't be able to talk about every single part of that today, but I wish we could, because I'd really like to. So hi, Mike.
Hi, Charlie. Thanks for having me. It's fun to be back for my second one.
Yes, Mike was with us once before, episode 16, September 4th, 2008. Mm-hmm. And even though it's been a while, if you're interested in this topic, I suggest you go back and listen to that podcast as well. I did this morning, and I think it was really great. So also with us today is Josh Goldberg.
Hi, Charlie.
Josh is a visiting professor here on summer sabbatical. His permanent address is Department of Neuroscience at Hebrew University in Jerusalem. And he's a neurophysiologist and computational neuroscientist who works on basal ganglia.
Okay.
Good to have you, Josh.
It's good to be back again.
We've done a podcast with Josh as well.
It was remote.
But that was remote, and during the days of remote podcasts,
right.
May they never return. And also with us is Francesco Savelli, one of our podcast regulars, an expert on hippocampus and spatial navigation and computer science.
Yeah, some of that.
And me, I'm Charlie Wilson. So, Mike, one of the things I think about reading your work is just the temporal graying of neuronal activity. So it's very common for us to study, those of us who have studied in vivo neuron spiking while animal is behaving, are used to thinking about behavior in little epochs of time. And we've usually created these epochs of time as a part of the experiment. This is where I present the cue. This is where the animal gets the reward. This is the animal's act that it has to perform. And then we divide up the time in each trial according to those epochs, and then we record firing rate during each epoch and say, well, this neuron fired during the cue. This neuron fired while the animal's running down the maze. This one fired at the choice point. This one fired. But it seems to me that at least in the cerebellum, what you're seeing is a finer scale of neuronal activity. So in one of these experimenter-defined epochs, like when the cue stimulus is being given, different neurons are firing in a sequence, and the sequence is meaningful. And part of the circuit function is derived from the fact that it is not homogeneous during that sequence. So could you tell us about that, about the particulars of that, how you discovered that, and what your
Sure.
Yeah, what your evidence is?
So we study the cerebellum. One of the ways we study it is that there's a behavior eyelid conditioning that taps into the cerebellum unusually directly. So two inputs to the cerebellum, mossy fibers and climbing fibers. There's two stimuli in this form of training. You play like a tone and then a little poke in the eye, little experimental poke in the eye. That activates, those two stimuli activate the two inputs. Learning happens in the cerebellum, and then cerebellar output drives the expression of the eyelid responses. The animal learns to close its eyelid when the tone comes on. Kind of a silly looking form of learning, except it taps into the cerebellum so directly that it's useful for us to study. So one of the things that derives from the fact that there's such a tight relationship between the stimuli that we use and the inputs to the cerebellum and the output of the cerebellum and the behavior is that the behavioral properties, the little nuanced behavioral properties of this form of learning, eyelid conditioning, tell us things about what the cerebellum does. So one of the things that we see in that behavior is that we play a tone, we poke the animal in the eye, metaphorically, and the animal learns to close its eye when the tone comes on. But there's more than that. If we vary the time lag between when we play the tone and we threaten the eye, the cerebellum doesn't just always respond the same way, but it actually has this clever trick where it can wait. And if the tone comes on 1.5 seconds before the threat to the eye, it'll wait and make an eyelid response just when the threat is going to happen. But if the tone and the threat are only 1/4 of a second apart, it won't wait. It'll make a much faster response. So the cerebellum has this way not only of encoding that the tone is on, but it has a way of knowing, well, how long has the tone been on? And so that extra coding means that if you freeze a moment in time, and you could look at the activity of the neurons doing the coding, you could tell not only that the tone was on, but you could infer how long it had been on, and that the learning neurons of the brain can use that extra coding not just to learn to close the eye, but to learn to close the eye at just the right time.
So is there like a group of granule cells, I guess it is, granule cells that we're thinking about? There's a group of granule cells that mean it is 50 milliseconds from the time that I'm going to get the unconditioned stimulus. And then on the next trial, that same group of neurons means 50 milliseconds.
Right.
And that is very reliable across neurons.
So it takes a very common way that we think in neuroscience, which is there's an input to a part of the brain, and that brain will use a layer of neurons to encode that that's happening. So we could say that a tone comes on, and there's some subset of all these billions of granule cells that when they come on, it means, hey, a tone's on. All we're doing, we're going to add to that the idea that instead of those neurons just remaining active through the whole duration of the tone, the cerebellum is designed to produce a richer code where there are neurons who fire just at the onset, and then granule cells that fire a little after that and a little after that. So that if you froze a moment in time, again, you could say, oh, the tone is on. The tone's been on for 1/4 of a second. Okay. Very important that not just that there's a changing pattern, but the pattern is the same every time you play the tone. If the pattern varies, if it's one pattern on the first time you play the tone, a different pattern on the second time, the cerebellum couldn't learn what to do. And so that's been a computational challenge, is that the old models that we imagined how the cerebellum does that turns out were incorrect. And the clue that they were incorrect is those models are very sensitive to noise. So a couple of stray action potentials here and there, and the pattern will wander off in a bizarre new direction, so that maybe the first 1/4 of a second so you can count on the same pattern, but then noise will make it wander off in all the different directions. And so our latest discovery that comes from a group at Harvard discovering a new synapse in the brain, in the cerebellum, is that there's a whole different way of telling time that is way less sensitive to those stray spikes. And so it's hard to tell time with neurons, but the synapse implements a kind of processing in the cerebellum where patterns can change over time, and you can count on them changing the same way every time you present a stimulus.
So does that require any learning, or is every time I hear a tone, regardless of whether it's followed by an air puff or a shock to my eye, my cerebellum is parsing that tone up into time slices?
Well, that's a great question. I think anytime a neuroscientist says something like, well, there's no plasticity in that part of the circuit, they're probably wrong. But as near as we can tell, if there is plasticity there, it's augmenting an existing wiring that's pretty static. So that, yeah, your cerebellum is designed so that for any given input, there's going to be a pattern.
So it means not just tones, but everything that happens, my cerebellum is breaking time up into little slices.
Interesting factoid, half of the neurons in your brain are cerebellar granule cells. So there's an old joke, we talked about this earlier, that they used to think that there were 40 billion neurons in the human brain until they realized there are 40 billion granule cells in the cerebellum, right? So literally half of the neurons in your brain are granule cells. So if it sounds like it takes a lot of neurons to do that task, well, here we are. There are a lot of neurons.
Yeah, so I have a similar question to Charlie's. So if you're teaching the same animal to, wait half a second and then a second and a half in 2 seconds, is it every time it's learning a new interval, is it programming another set of cells that are going to have their own pattern, or is it building upon the one that does half a second, then they add another one? And then if you come back and ask it to do half a second, does it pull up the old pattern it learned initially to code half a second?
Those are good questions. So this is an oversimplification, but we can imagine that there's a part of the cerebellum that is creating patterns. And its job is just to create these patterns so that I can look at the pattern and know how long the tone's been on. Then there's the part of the cerebellum that uses that pattern to learn. And in fact, the main learning synapses in the cerebellum are between the neurons generating the pattern and the neurons that make the output of the cerebellar cortex. Right? So my answer to your question is it's the same pattern every time, but if you trained the cerebellum to make a fast response, in other words, that would involve changing synapses that are of the neurons that are active early in the pattern. Now, if you retrained the animal to make a response to the same tone but later, it would be the same pattern, but now the changes in synapses would be the synapses of the neurons that are active late. So the pattern's always there as a template, and then learning says, well, let's respond to that pattern, or let's respond to that part of the pattern, let's respond to that part of the pattern to make... It's the same thing. I could answer the same question if there was no timing here, but we were talking about learning to different tones. You would say, well, there's a 1 kilohertz tone activates some neurons, and those synapses change for that. A 10 kilohertz tone activates some other neurons and changes in their synapses. So now it's the same tone with a pattern unfolding in time. You want an early response, you change the synapses of the early firing neurons. You want a later one, you change the synapses of the later firing ones.
So the granularity of these time slices is then fundamental. It tells you how quickly in time things can be responsive. So what is the granularity of that? What are the durations of activity of these granule cell groups?
Well, we only know this from guesses from simulations because granule cells are notoriously one of the most difficult cells to record from in the entire brain. So we can record from them in slice, in vitro, and learn their physical properties. It's almost impossible to record from them in vivo, in an animal. It's one of the reasons, Charlie, that I started doing these computer simulations. That we had ideas about granule cells, and we can't record from granule cells. But granule cells are really simple, and that makes them amenable to building accurate, sort of biologically reliable, faithful simulations. And so we resorted to simulations to say, well, if we could record from them, what do we think we would see?
Isn't that something? Every part of the brain has its gotcha.
Nope.
So there's some parts of the brain where you can record the neuronal activity, but they don't have any straightforward relationship to behavior.
Right.
The place where you have this wonderful relationship to behavior, and then there's some crazy circuit that you can't sort out. The cerebellum has this great circuit that we understand pretty well, and great relationship to behavior and to sensory stimuli, and then one of the most important neurons in it.
Intractable.
Yeah, intractable.
Right. So, but if you let me use my simulation behavior as the basis for my answer, and then say that even if I didn't have that, we can kind of infer the granularity by... So one way that you could infer that indirectly is how fine-grained of temporal discriminations can the cerebellum make? If you train the cerebellum to make a response at 200 milliseconds, can you use a different stimulus and make 210? So there's a limit to the granularity of the output. So if I combine those two things, the insights from the simulation and indirect guesses from the granularity of the output, things are well, and then there's a complexity. Early in a stimulus, things are changing rapidly. Like every 50 milliseconds or so, we're probably mostly different set of neurons. But both from inferring from behavior and from the simulation, the turnover slows down as any input is on. So the turnover, like 1.5 seconds into an input, the turnover is slower than it was a quarter of a second in. You see that in the behavior, And this is true seemingly of all things that the brain times. It's called the Weber function, which is the temporal discriminations early. It can be really precise, and they get less and less precise with time. Mm-hmm. And the cerebellar timing shows that as a beautiful example. So, and when we train the cerebellum to make responses in a quarter of a second, it's like a robot. It's like the jitter, the temporal jitter, and the onset times of the output are a few milliseconds. If we train the cerebellum to delay a response for a second and a half, the jitter is several hundreds of milliseconds. So, one time the onset is 120 milliseconds, one time it's 140, one time. And so if we combine those things, the early turnover is on the order of 50 milliseconds, and then eventually it becomes more like a couple hundred milliseconds.
It's the same with the place cells also have been shown to be able to kind of work like as a sort of stopwatch collectively. Mm-hmm. And so like the first cell during a behavioral task where the animal has to wait, so there is a waiting period, and certain cell fires at the beginning, and then later and later and later, and the later you go, the less precise become these kind of receptive field in time, so to speak. That's just kind of.
So what's the size of that receptive field in time? What is the time slice?
Well, so I think people have done it mostly like up to 10 seconds. There was one study going beyond, but most of the studies, like after 10 seconds, you see really the time interval at which the later neurons, the neurons that fire later, they tend to kind of become very, very fuzzy. And
I was just wondering if different parts of the brain are timing different things, like cerebellum is timing things that are 250 milliseconds long, and
it's faster.
Timing things that are
that's like that's kind of the it's about, I think, 10 seconds, like that's the time scale. And then it becomes, in my opinion, it starts becoming very unsatisfactory, when you really look at the raster plot.
That's 5 times slower than Mike's data.
But,
But you introduced this whole topic by talking about how people like to divide up their recordings into time epochs. And so one interesting thing, if you start to appreciate that there can be some jitter in when neurons fire, or that there might be different, within a layer of neurons, there might be neurons that firing at different times. It really speaks to the danger of averaging across many trials, because we get this temporal averaging effect. So a neuron might have a very precise burst of activity, but if the timing of that burst varies, if you average all of those, what it'll look like is the neuron ramps up slowly and ramps down slowly, which does not reflect what the neuron actually does. Or if you average several neurons together, say in a multiple unit recording, if one of them fires early, or one of them fires in the middle, and one of them fires late, what it's going to look like is all of the neurons were tonically active through the whole epoch. So time is a real enemy of the way we love to average responses and to make peristimulus time histograms. Any jitter or variability in time is a real killer. It can give us peristimulus time histograms that lie to us about what's really happening with the neurons.
So we need cells that fire really quickly so that we can get a lot of data out of a single trial. Because otherwise we're either averaging across neurons, which you just said is going to give us an error, or we average across trials with the same neuron, which is going to similarly give us some trouble.
Yeah, I didn't say there was a solution. I think we do need to be cognizant that when you see a PSTH, there might be an averaging artifact. The neurons, on any given trial, its response is not going to look like your histogram.
It's like a difference between precision and accuracy, right? The engineers draw that distinction. And so it's like, if you don't have the ability to disentangle those things, you don't really know whether it's uncertainty across trials versus it's really uncertainty coded within a single trial, like at that given moment in the brain.
So how does that connect up to learning the eye blink? And I'd like to point out, you said metaphorically poking the animal in the eye, and you're really not poking the animal in the
Well, in the old studies, people would literally puff a little air in the eye. which the rabbits, don't like.
Uh-huh.
Many years ago, we implant stimulating electrodes in the skin, and people say shock. It's not. It's not. We just stimulate it. If you do it to yourself, which I have, it feels like being kind of thumped on the forehead.
That's why you say.
Right, and so it's not painful, but it's a threat. I think the teaching input to the cerebellum encodes that as a threat to the eye, so we better learn something.
So this is a tactile stimulus near the eye.
Yeah.
So the task is a tone comes on at the end of that tone, and we've been worrying about the time because the tone might end at different times. And then there's this stimulus that makes you blink or makes the animal blink. And the blink moves earlier and earlier in time, but it doesn't move arbitrarily early in time. It'll shift a certain distance and then become stable.
Yeah.
And that's the timing.
That's right. So if you looked at the response of an untrained animal, all you would see is just a reflex response that follows the tap on the eye. In a trained animal, what you see is that the response begins before the tap. That's the learned part. It's anticipating. It's responding to the tone and not to the tap stimulus. But the timing that we're talking about means that it just precedes the tap. So that if there's a very short time interval between tone and tap, then the response happens quickly. If there's a longer interval, then you would see the animal just sit during the tone, just sit there, and then respond right before the tap. So it's an example of, or an illustration, let's say, of how what the cerebellum's main job in life is to predict what's about to happen next, all right? So this little training we do, tone, tap the eye, the cerebellum is learning that, in my experience, a half a second after this tone comes on, we're going to get thumped in the eye. So why don't we start closing our eyes 400 milliseconds after the tone, and then we'll be safe, right? And so because it can learn to predict what's happening next, we see this timing.
So I'm curious about one thing, as you extrapolate on this idea that, it predicts things, and you give us the example, walking, and so the cerebellum then should be able to keep track of multiple timelines at the same time, potentially staggered or overlapping, because there is a lot of things going on, right? But so I'm trying to going back, making sure I understand the idea that is behind this idea that the cerebellum creates these patterns. But it seems like and that evolve over time, and so based on and that part is kind of fixed, right? So the pattern that evolves is always the same. But then if you have to track multiple timelines, is it different parts of the cerebellum keeping track of different timeline, or we need to rethink that particular part shouldn't be hardwired? Or how do you think it works if?
Yeah. I think that's a really good question that allows us to back up and to remind ourselves that we do these experiments. We isolate things so that we can control them. So it's a very atypical thing that the cerebellum would do, where there's one input happening. But we do it that way because that lets us infer the rules for how it does things. Once we know those rules, now we can go back and watch an animal behaving like we are right now, which is there aren't these punctate stimuli that come on. The stimuli to the cerebellum, there's just stimuli constantly happening. But we can take those same rules, we know those same capabilities are in there, but it's not always the case. In fact, it's rarely the case that what the cerebellum has to do is, I've got one input and I'd better time it till just the right time. So a lot of times, for example, I would imagine that the cerebellum's it's much easier than our experiments for the cerebellum to make the response at the right time, because there might be an unfolding pattern of the inputs. And all it has to do is respond to the last input before the trouble. Our experiments show, if we strip away everything and just look at one input at a time, what are the rules for how it can do things? Does it need to do all those tricks every time? No, but those tricks are there in case it needs to. So my answer to your question is, the pattern of mossy fiber inputs to the cerebellum is always changing, and the cerebellum is reacting to it and making patterns so that it can say, lift up your arm, don't do this, sit, close your eye, whatever it needs to do. But in eyelid conditioning, we've stripped it away. We've given it one time invariant input and say, well, what are the rules that you can do with that?
So there are some specializations so that neurons that are responding in this eye blink conditioning may not be the same cerebellum neurons that are firing when I'm moving my hand and something happens. Is there's some kind of topographic organization for that?
Yeah, so imagine what we're talking. So we're talking about eyelid responses. Imagine that there's a part of the cerebellum for every movement that you can make. And so the idea of these simple experiments, like who cares about eyelid responses? Honestly, I do not. Okay, but using these eyelid responses, we can infer the rules for how these parts of the cerebellum work. And the idea is the rules that control the parts of the cerebellum that controls your reaching are the same as the rules that we reveal with the eyelid. But there's a motor map in the parts of the cerebellum that are motor, which is not the whole cerebellum, but the parts of the cerebellum that are motor, there's a map. There are, and it's a funny thing about the cerebellum, but all of the neurons that care about one movement are arranged in long skinny stripes called parasagittal stripes. So there's a stripe for eyelid responses. When we're implanting our electrodes, we can be really sloppy in the X direction. We have to be really precise in the Y direction because the stripe is kind of skinny. Okay, the map is these series of stripes, and each stripe has its own motoric thing that it cares about.
Well, it's not very uncommon for us to have to time a hand movement or a finger movement, and something tells us that time is coming, and then so it's not that unusual with that.
Yeah, I don't think we realize how much time comes into play for the accurate. So, I was a baseball player, so so when a pitcher throws a ball, the difference in timing of the release between a low pitch and a high pitch is a few milliseconds. So the cerebellum of pitcher has to be able to say when it's a low pitch, we have to release the ball 4 milliseconds after when we release the ball for a high pitch, right? And so just imagine anything precise, and particularly precise and fast that we do. Timing, knowing exactly when to twitch the muscles is important as which muscles we twitch and by how much.
So I had a related question. So your experiment you've been using is sort of a stimulus response experiment, but as we were discussing earlier, and just mentioned now, is that the cerebellum is supposed to plan out these, smooth movements and reaching. So have you ever experimentally checked whether this generalizes to self-initiated movement or some other form of learning or training where you could see whether it still uses the same rule? You're assuming it'll be the same thing, but have you actually tested it on another kind of task that isn't?
Well, not my lab, but one of my favorite corners of cerebellar neuroscience is another very natural behavior that people have used with great success to study the cerebellum is this vestibulo-ocular reflex that we have, that we don't think about, but we have a reflex that none of us think about. And when you move your head to the right, your eyes naturally move to the left by exactly the right amount, so that you're looking at, I'm looking at the camera, and if I move my head back and forth, my eyes are moving exactly the opposite direction, so that my gaze remains on the lens of the camera, right? The accuracy of that reflex is controlled by the cerebellum. The cerebellum can learn to increase or decrease how much the eyes move when the heads move. So I was talking about this with the students earlier. I'm looking at the camera, I move my head back and forth, and the camera's not moving because my eyes are moving. But that changes the optics. Now when I do this, the camera's jumping when I move. In about 10 minutes, if I keep doing it, it'll stop jumping. That's the cerebellum learning, okay? It's a very different form of learning than eyelid conditioning. It's natural. Eyelid conditioning's not. But I can tell you that my buddies who study that form of learning, we get the same answers. Steve Lisberger and I wrote a review article together years ago saying what we learn about the cerebellum studying the vestibulo-ocular reflex is the same that we're learning from the cerebellum when we study eyelid conditioning. We wrote a review article saying it must be right because we're getting the same answer studying two completely different things. But in the end, we sacrifice, you have to use your imagination to plug what we study into the real world. What we gain is all this control to study the rules. You know, I can tell you the rules about how it, you know, how long of a gap can there be between a mossy fiber input and an error before it'll learn. So we can learn all those things. So we sacrifice, well, we accept artificiality to gain rigor and control and mathematical definability. But then it's wonderful to have other people studying the cerebellum where maybe they don't have as much control, but they have more relevance. Mm-hmm. And when we notice that we're thinking the same way, then I think that's the check that, you know, maybe we're not barking up the wrong tree.
So I want to ask another question, changing the tone. How ancient is the cerebellum?
It first appears in fishes. And from fishes to amphibians, the wiring of the cerebellum isn't quite the same, but all mammals, to be sure, the wiring of the cerebellum is well, I'm sure there are small differences, but they're not the kind of differences that make you wish that you studied humans instead of, you know, rabbits. So it's the nice thing about studying an old part of the brain is that the relevance of mouse studies to humans is more assured than, you know, a lot of the things that we do.
So I'm wondering, I know it's hard to answer questions about how to generalize, and you've just been telling us why you don't want to do that too much, but with everything you've talked about is a sensory motor thing, and you said there are parts of the cerebellum that are motor and parts that aren't. So is there an analogous thing that the cerebellum does with non-motor, maybe just pure sensory stimuli without any motor component?
Yeah.
Or?
Well, thank you for prefacing your question by saying you can speculate, because that. So I think the most useful way to approach questions like that is to focus more on the computation that the cerebellum does, right? So I think what eyelid and other behaviors reveal about the cerebellar computation is that this learning is in service of improving predictions. That the cerebellum's job in life is to get input from motor cortex and from the body and proprioception, and then given that, predict how do we twitch the muscles to do it just right. And the whole thing with climbing fiber-driven learning in the cerebellum, even the properties of that learning are clearly in service of, I made a prediction, it was wrong, the climbing fiber loops back and informs me of that, I make some synaptic tweaks, so next time when I'm in a similar situation, I make a better prediction, okay? So learning, the cerebellum learns to make good feed-forward predictions. Feed-forward predictions are important because when we have to do things quickly, there isn't time to get started and make an adjustment. So for our fastest movements, we can't start and then adjust on the fly. We have to decide ahead of time, how's this movement going to go? So you have to predict. Predictions have to be accurate. That's why you have to have learning to, you know, make a better prediction when you screwed up last time. Right? So that's the motor world. But I think what we can do then is just take as our ground truth that the cerebellum does prediction. Now, in the humans, like more than half of the human cerebellum, those predictions are going back up to different places in cerebral cortex, and we don't know what they're used for. I'm willing to believe that a starting place is that it's still feed-forward predictions of the same time scale with the same learning to learn. Now, so what we need to figure out is what's being predicted, and how is the prediction being used? Okay. So we have indirect hints. So if you go to functional imaging, which is the kind of an experiment you can do in a human, you find that the cerebellar output, the cerebellar nucleus that has all the output that's going to cortex instead of down to the spinal cord. So what makes it active? Well, one of the ways that you can most make that part of the brain really active is in the so-called word selection task. So here's the setup. You're in the magnet. They're measuring what parts of your brain are active, and the instructions are something like this. You're going to hear a sentence read to you, and the reader is going to stop when it's time to pick a verb, and we want you to imagine an appropriate verb for that sentence. And they take the snapshot, the activity snapshot, right when it's time to pick the verb, and that lateral part of the cerebellum, it's like crazy. So I imagine that that's consistent with the prediction thing, that what that part of the cerebellum is saying is, given where we are in the sentence, I predict the next word ought to be X.
Wouldn't it be something if studying idling conditioning was the key to understanding language in humans?
See, I've talked about this, and I think I get blank stares sometimes. You know how much I respect you intellectually, so it thrills me that you think that way. But I have argued many times that and the basal ganglia is the same way. There's cognitive and motor functions of the basal ganglia. It's inherently easy to study movements, so we can use movements to infer the rules for what's going on there. And then if the same part of the brain is using a prediction in service of movements and predictions in service of cognition, we have a foothold. We know what the computation is that's being delivered to that cognitive process. I think it's exhilarating to think of it that way.
Well, now you have Chat GPT, right?
There you go.
The technology is basically an expansion of the technology that would, complete your sentence up to a few years ago, and now it can complete the entire essay.
See, it's funny.
Essentially, and it's like, now maybe if they give you that stare, you got something to tell.
Well, people get weirded out that Chat GPT is somehow sentient or something, but it's just a big correlation that it's scanned the internet, and it knows that following these 4 words, the 5th word ought to, and it's surprising how natural of sentences it can produce doing just that trick. And if my little thing about the cerebellum is right, we may be doing something not so different. Given the 4 words that I've just said in this sentence, the cerebellum could say, well, a good 5th word to complete your thought would be.
So I actually,
there's my prediction.
Go back to podcast to listen to Karl Peter Meyer telling us exactly that about chat,
Nice.
GPT, and human comprehension. So this is a very good place to end. So thank you very much, Michael Mauk,
Thanks for having me.
and
It's fun.
Josh, and
thank you.
Francesco.
Absolutely.
This has been Neuroscientists Talk Shop.
One request. It was 15 years. Can I come back sooner than 15 years?
Absolutely.
Cool. Deal. Thank you for having me.
Thanks for coming.